Activation functions. This tool helps us visualize some common activation functions and their behavior in terms of input and output. An activation function is a crucial component of a neural network that helps introduce non-linearity and enables the network to learn complex patterns and relationships in data. Think of it as a mathematical function that takes the weighted sum of inputs from the previous layer and applies a transformation to produce an output for each neuron. It acts as a decision maker, determining whether the neuron should be activated or not based on the input it receives. Activation functions like the sigmoid function or the rectified linear unit ReLU function are commonly used. Let's see how the activation function works in the context of neural network architecture. This is a basic neuron, and it has some inputs, x1, x2, and x3, which are fed to it weights w1, w2, and w3. Then the weighted sum is calculated as sigma xi wi. Next, we apply the activation function, which produces the output. This output is either the final output or it's fed into the next layer of the network. There are several different activation functions available because different functions have unique properties that make them suitable for specific tasks. Some functions, like the sigmoid function, can squash the input values between 0 and 1, which is helpful for tasks that involve probabilities or binary decisions. Other functions, like the rectified linear unit, or ReLU, are simpler and computationally efficient, making them effective for many reasons. This tool will help us visualize some common activation functions. Let's explore it. Please note that the credit is provided to the tool's author and its Git repository. Here we have a drop-down with various activation functions, including linear, sigmoid, softmax, and so on. Next, we have some function parameters related to weight and bias, and I'll explain these in a minute. These parameters can be changed using these sliders or the text box spinners here. Next, we show how the function can be plotted. And finally, we have the range of input values that can be set using these spinners. Please note that all these activation functions have their corresponding mathematical expressions and functions, which you can easily find online. Now let's come back to talk about the weight and the bias. The bias is responsible for generating the output by adding or subtracting a fixed value from the input. The weight is like a multiplier that is applied to the input before generating the output. In real-life applications, the weights and biases are part of the neural network configuration and training. The first activation function we'll cover is the linear function, which is the simplest function of all. So if we set the bias to 0, and I can do that by using the spinner, and we can leave the weights as 1, this means that the function will produce an output equal to the input as depicted by this graph. So if the input is 2, the output also turns out to be 2, and so on and so forth. Now, if we change the weight to 2, again, we can use the spinner. Now, we'll notice that the output will be 2 times the input. So again, same example. If the input is 2, the output turns out to be 4. And this applies to other input values as well. Using the input selector, we can increase or decrease the range of input values. So I can change this -5 and bring the input range from -10 to 5. Let's refresh the page to get back to the original view. Now let's select the sigmoid function. So select sigmoid from this dropdown. And please note how this function looks when plotted with a weight of 1 and a bias of 1. When we input a number into the sigmoid function, it transforms that number into a value between 0 and 1. Think of it as a way to map any input value to a probability-like output. The sigmoid function has a distinctive S-shaped curve, which means that a small input value are squeezed towards 0, and large input values are squeezed towards 1. The middle portion of the sigmoid function, also known as the linear region, is an interesting section where its behavior approximates that of a straight line. In this region, the sigmoid is more sensitive to small changes in the input. Again, as in the previous example, we can change the weight and bias to see how they affect the behavior of the sigmoid function. So I'll change the weight, I'll bring it higher, and I can bring the bias down, and we can see how that affected the sigmoid function. Here are some other activation functions that you can view and analyze, such as tanh, ReLU, we have soft plus, and many others. This covers how this tool can be used to visualize activation functions. Please feel free to explore other activation functions and analyze their behavior by changing the weight and bias values, as well as the input range.